recording. We'll start soon. Okay. I do one more thing before I start. Have you done the assignments? Any assignments?
No.
Okay. Try to do a couple of them today, right?
Yeah, I'll do it after this.
Yeah. It shouldn't take much time, but at least you should be carried forward with those. One more thing left. Screen and camera. Record. Microphone. Not recording. Entire screen. Window. No. Entire screen is correct. Share. Okay. All right. So I can start presenting. Chrome tab. Entire screen. This one will be good. I think so. Okay. Can you see my screen now?
Yeah.
Alrighty. This is from where we have done yesterday. Okay, we were at, actually I took some time to manage your courses relatively with maths and physics. So these are the mathematics tab, and this is physics tabs that we need to cover at least whatever is mentioned in level 12. Oh, sorry, level 2 and level 3, right? Okay, so we good. We were in the last, some of the factors, and then Okay, we finished that over here. The magnetic field from each of the turns in the coil add together, so the total magnetic field is much stronger. This produces a field which is similar to that of a bar magnet. A coil of wire like this one is often called a solenoid. Moving charges can create magnetic field like this, and then we have done the inside and the outside one, right?
Mm-hmm.
The magnetic fields coming out of the piece of paper, we use dots, and drawing magnetic going into the paper, we draw crosses. Oops. Oh, my mobile. It's doing good. Just a second. Keeping aside. Sorry about that. Okay. So we were at last magnetic field exert forces on individual moving charges. This may be calculated by F equals BQV, where B is the magnetic field, Q is the charge, and V is the velocity of the charge.
Yeah.
Right? Okay, to find the direction of this force may be worked out by the using of Fleming left-hand rule. So there are a couple of rules that uh, we need to learn about regarding the directions of the force itself, the magnetic field, and the movement of the charge of the electricity kind of thing,
Mm.
right? So out of those, this is the first Fleming's left-hand rule. Left-hand rule. If you point like this,
Yeah.
right? Is this your left hand?
Yeah.
Okay. So the thumb is the motion of the electron
Okay.
or the charge itself. Okay. This is the field,
Uh-huh.
right? This is the field, and the perpendicular to it is the current. Okay.
Okay.
So the motor effect can be used to induce movement in a wire, and then it comes. So, for example, the current in the wire is moving like downwards. Magnetic field is moving, and the force on the wire is on the perpendicular to that thing. So let's demonstrate. Oh, I forgot to add that tab as well. Okay. We're doing this. Here. Okay. Now, there is another rule which is called magnetic force, the right hand rule, and it's depend upon the slab kind of thing, right? It's not about the fingers, it's using the slab. So if
Okay.
you can like this, point it out, the force
Mm-hmm.
perpendicular to it in the thumb's direction is the movement, and the magnetic field can be in any direction in that plane. So the thing is that the magnetic field and the movement of the charge are the same plane, but
Mm-hmm.
the exerting force is perpendicular to that plane. If we have a slab as a plane where the magnetic field and the charge are moving, this may be the perpendicular to it, 90 degrees. Okay. Okay. So that's why it is here. Key points. Uh, everything is covered up here. Okay. Now, from this topic, from this electromagnetic induction, you can say we come up with sorry, here magnetic field exerts forces on charged particle in motion. So the point is in motion. If the charge is static, it's not moving, there is no magnetic force will be exerted. Okay.
Mm-hmm.
It is only a magnetic field exert forces on charged particles in motion. If they are in motion, then only the force will generate them. Okay, and
Right.
that is equal to F equals BQV, right? There is some interesting facts and figures over there. Let me introduce to that too. Yeah. So again, here we can see that B equals F by QV sine theta. That is the magnetic field, right? I already told you that the magnetic field strength unit of magnetic field strength is Tesla,
Yeah. Yeah.
right? Okay, and then so because sine theta is unitless, the Tesla is, so this is an easy way to get the units, okay, the formulate the units of physical terms. How? For example, if we have 1 Tesla means 1 Newton, that is the force unit. Then, as we already know, for the charge it is coulomb, and for this V, that the speed, we have meter per second.
Okay.
Okay, as we have already seen in the cars, it is kilometer per hour. So that's a distance unit over the time unit, right?
Hmm.
For this calculation, we are using meter and seconds as a time. Okay.
Okay.
Now, where the A came from this to this, I can explain that. Okay. A is the ampere. That is the I. Okay. The current. Okay.
Yeah.
Let's see where it comes from. Okay. Okay. So I'm just copying this and see that I can copy it here or not. Okay, that's nice. Is it for me? Okay. All right. So this is like 1 Tesla equals 1 Newton over Coulomb with the meter per second, right? So I can write it down here. It's not, doesn't make any sense. I just remove it. So where is my, okay, this one is. So 1 Tesla equals 1 Newton or force. Okay, first, let's bring that thing first. So B equals F over QV, right? So this is what we are taking care of it. I'm using sine theta 90 degree from the equation 1, right? From
Hmm.
there, we are already, so we are not bothering at this moment, we are not bothering about the angle between the magnetic field and the speed, right?
Okay.
Or the motion of the charge. We are assuming that it is 90 degree.
Yeah.
Then for B, it is 1 Tesla. I'm just replacing the units equals 1 Newton over Coulomb multiplied by meter over second, right? So this is the actual representation where it says, where it says 1 Newton over Coulomb multiplied by meter per second. So meter per second, again, it's an over the meter or
Yeah.
below the meter. That's the second we say. All right. From equation, we know, have I mentioned somewhere? Yeah. So from here, we already know that ampere, which is the current, equals Q over T, that is Coulomb over second. So we can replace in this equation, let's say this equation is 2. right? So now I can use text. So from equation EQU equation 2, we can say that, what we can say, or we can put it in something like this, equals 1 Newton over P over second, right? Multiply by meter.
Okay.
Is that correct?
Yeah.
So therefore, we can say that A equals column over second. Replacing this in here, we can say that 1 Tesla equals 1 Newton over ampere multiplied by meter. So 1 Tesla equals Newton per ampere meter.
Okay.
Okay, so
Yeah.
Tesla equals Newton per ampere meter. That's the what we conduce from this equation. Okay, let's bring it some smaller. So other than, for example, a bigger figure we have kilogram, the smaller is gram, right? We have bigger units like kilometer, or then the smaller one is the meter one, or the centimeter or millimeter, right? Similarly, for the charge, there is another smaller unit which says Gauss, G, which is equals to 10 to the minus 4 Tesla. Sometimes we use it. Interestingly, the strongest permanent magnet have fields near to 2 Tesla. Superconducting electromagnets may contain 10 T or 10 T, 10 Tesla or more. Earth, Earth's magnetic field on its surface. Earth's magnetic field on its surface is only 5 to the power 5 into 10 to the power minus 5, or it's just like 0.5 Gauss,
Yeah.
right? Okay. This we have already seen that F is perpendicular plane of the movement of the charge and the magnetic strength of the magnetic field strength. Okay, that's the right hand rule to get the uh, to get the force, direction of the force, direction of magnetic force on a charge. Okay, we have already done that. That's good. On one way to remember this is that there's one velocity represented according to by the thumb. There are many field lines represented. Okay, now we can demonstrate this one with our yes. I need this, not this one. Where is that? Yes. Okay, I need to put them as also in the magnet. Okay, we have already demonstrated that yesterday, that this is perpendicular to this one when we have the 90 degree.
Yeah.
So almost the B is equals to uh, by. That's the one thing. Let's do something. Mm, magnets and compass. Okay, magnets and electromagnets. Electromagnetic. Okay, we have put a 10-volt cell.
Mm-hmm.
This is the direction. Okay, so you can see the direction, and now here we can see the magnetic field, right? And let's say from here to here, it's quite understanding that it is something like that, it is moving. Okay, let's minimize the volt. So once the voltage is there, there is no magnetic field. Why? Because magnetic field will only induce when there is a charge moving,
Yeah. Okay.
right? So when there is no volt, no charge is moving in the wire, that's why there is no magnetic field.
Okay.
Okay. Okay. Now, if we increase the charge, as soon as we increase the charge or the voltage, that means the charges are moving,
Mm-hmm.
right? And they are inducing the magnetic field. So B is from here, we can see the B is the magnetic field. Loops, we can increase the loops. So as we increase the loop, there's only 4 loops. Okay. Let's decrease. What's happened when we decrease? You see the power of the magnetic field.
Yeah.
It's a field meter, we can say. Let's have a field meter. Now you can see the less the gauss, the less the coil, the less the magnetic field. Let's now increase the. It's increased as such 1.64. Okay, 246. Right, so it's quite increasing. As we are increasing the number of coil, the magnetic field is also increasing.
Okay.
All right, so what else we can do here? Let's see. There is one more thing that we can do. Oh, we already done that thing. Okay, cool. So I hope we are nearing to complete. Mm, Okay, let's recap what we have done so far. Magnetic fields exert forces on charged particles in motion. The direction of the magnetic force is perpendicular to the plane formed by V and B as determined by the right-hand rule. SI unit of magnitude of the magnetic field is called Tesla, which is equivalent to 1 Newton per ampere meter. Can you repeat? Tesla equals 1 Newton per ampere meter.
Tesla equals 1 Newton per ampere meter.
Correct. Sometimes the smaller unit, Gauss, that is 10 into minus 40 is used instead. So this is when the expression of the magnetic force is combined with that of electric force, the combined expression is known as Lorentz force. Okay. Now, as we have seen that the electrons are moving, that means some force is exerted on the electrons to move, right?
Mm-hmm.
And there is also a magnetic force is also created by the moving of charge. So combining these two forces, the electric force and the magnetic force, that's known as Lorentz force. We will see if it is other than this statement is mentioned somewhere else. Otherwise, we should be just touching up this thing. When considering the motion of charged particle in a magnetic field, the relevant vectors are the magnetic field B, the velocity of the particle v, and the magnetic force exerted by the on the particle f. These vectors are all perpendicular to each other. So again, vectors are the vectors are the terms which has not only the magnitude but the directions as well.
Okay.
Okay. Okay, states this is this. That's a correct. The direction of the force on a negative charge is in the opposite sense to that above. So pointed away from the back. Okay, we can do that. Key terms: Coulomb force, the electrostatic force between two charges, as described by Coulomb's law. We haven't done the Coulomb law, right? Um, yes, we will do that. This one. But let's see what we have there. Okay. Condition in a space magnetic field is already Tesla. We already know the international unit for the magnetic flux density or magnetic inductivity symbol is T. Again, now the terms got changed somewhere around, right? Here we know that the Tesla is the unit of the magnetic strength, magnetic field strength. B, B. Okay. Magnetic field strength, which is equivalent to magnetic field strength, is equivalent to magnetic flux density or magnetic inductivity. Okay, that means flux density or magnetic inductivity is that how much it take to uh, the pull or push in between the magnetic field, wherever the magnetic field, how hard it is to pull or push in that particular. So that's the either we can say magnetic strength
Mm-hmm.
or magnetic flux density or magnetic inductivity,
Right.
right? So this is the last thing that we okay. Now we have these things. Without knowing anything else, we can't do much because it's not clear here that what notions they are using. Is it the voltage? What I'm saying is that F equals to BIL. L is the length of the solenoid,
Mm-hmm.
that wire. I is the current which is being flown, the current in the wire,
Yeah.
and B is the magnetic field which is applied here.
Okay.
Okay. And then moving a current carrying conductor through a magnetic field can induce a voltage, more correctly termed as EMF, electromagnetic force. This may be calculated by BVL. Again, it is the length, it is the speed,
Yeah.
and this is the magnetic field.
Okay. Cool. Okay.
Okay.
Yeah.
Let's see if we can come up with these two, but at least for now, we know this much only. Okay. All right. So this is what the level 2 of physics as per uh, we made some touch ups over here. Okay.
Yeah.
All right. Now I think we need to focus on these two terms, F equals BAL and V equals BVL. Let me find that and we will continue from there.
Okay.
Mm, distance, basic flux and flux. No, they haven't mentioned in detail somewhere around here. I need to find it out here only. To false and cause law. Let's see if I can find here and here. No, they haven't mentioned that. Sorry, wait just a second, please.
Yeah, all good.
Okay, here it is. That's the Lorentz force, and EMF, that is the voltage. EMF is EMF is BVL. BVL is it the thing? BVL. 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 Yes. Got it. Yes. Okay. So it's a being a long chapter according. So basically, what they are trying to say over there is there is lots of laws and related to magnetic flux, induction, and Faraday's law. This
Hmm.
has been explained over in these two lines only. Right? This in this they are trying to say something else. Right? They are mentioning something V, which is not the voltage itself. It is the EMF, electromagnetic flux, right? Even though this is like the same that we have said already, that this is the magnetic field strength, this is the velocity, and this is the length of the rod,
Yeah.
right? Similarly here, the force induced. So this force is not something which is we already seen in here, right? This
Hmm.
is the electromagnetic induction. This is the force uh, that exert on the magnetic field with the moving charge. But here, if a length of if a rod or conductor, you can say, of length L, which moved within a magnetic field, that's the force we will face to move that rod from left to right or right to left within the uh,
Uh,
within the magnet.
okay.
Okay. So
Yeah.
that because what is happening is, as we said that already, that when we put any rod, magnetize that thing, magnetize the rod by pointing or putting voltage around those points. So it will again, because the current is continuously moving.
Yeah.
So that means it also has its own magnetic field,
Okay.
right? And that magnetic field, when we have two, now there are two magnetic, one is the external magnetic field,
Hmm.
and one which is induced by the current, the moving current, the current flow, okay, on the rod. So assuming this, let's go to that simulation. Mhm. This is the simulation, yeah, electromagnetic. So see, so when this thing is happening,
Mm-hmm.
right? So what if we point, I don't know that if we can current source. Okay, that's interesting. Okay, I can just move a bit, slow it down like this. Okay, so now we see that there is a magnetic field here, right?
Yeah.
Within this one. So what if I can put another magnetic bar near to this magnetic field? What happened to that? Then I have to exert some extra force
Mm-hmm.
to move that magnetic field, move that magnetic bar,
Oh,
external
okay.
magnetic bar,
Yeah.
right? What if we have a external magnetic bar, but now there is a rod which is moving within that magnetic field, but the current is also flowing in that,
Right. Okay.
right? So,
Yeah.
for example, here, what they are trying to say is that the current in the wire is flowing,
Mm-hmm.
but we are also moving it. We're trying to move this wire within that magnetic field.
Yeah.
So this force is calculating. This force is calculated by BIL, the amount of the ampere, the magnetic field, and the length of the wire. And this electromagnetic flux is something else here. See, this is what I want to say. Okay, let's go through with this one by one. Like 10 minutes, and then we will finish this up. Let's complete this one. Okay, induced EMF. EMF is electromagnetic flux.
Okay.
All right. So in this, we had the battery, as we already seen that thing, and this is the coil, you can say, right?
Yeah.
And this is the galvanometer. Demonstrates the magnetic field can create currents. The following figure, when the switch is closed, a magnetic field is produced in the coil. So again, magnetic field is produced in the coil on top part of the iron and transmitted or guided to the coil at the bottom of the part. It's moving. The galvanometer is used to detect any current induced in a separate coil on the bottom, right? So this is the coil which is being wrapped up.
Yeah.
So this wire which is conducted in the using with the battery, and this is the wire which is connected to the galvanometer. So we create the current in this coil, but there is another current which is induced in this coil, the below one.
Yeah.
Okay.
Okay.
And now there is another term, magnetic flux, magnetic flux, often denoted as phi or phi b. This is the b that we have already know. Through a surface is the component of the magnetic field passing through that surface. Again, that is the value which is being induced by the magnetic field, moving magnetic field, that how that particular area is covered up.
Okay.
I can try to make you something more interesting by this one. So this is the electromagnetic flux. Change in flux itself. Second EMF is greatest when the charge change in the time is smallest. So here what they want to say is that we can't induce current by just moving some magnets here and there,
Yeah.
right? It is only okay. What happened? I can show you some interesting story about Faraday, because he is the person who introduced this logic, or who explained this whole phenomena. So what he is doing is that he has its own coil, right?
Yeah.
Own coil, and which is connected to the galvanometer, something like this. This is the aperture that he has used, right?
Yeah.
And what he believed that, because, for example, we already know that moving a coil within a rod can create a magnetic field,
Yeah.
right? So he want to see that when a magnet moves, can it induce the electricity or not,
Mm,
electric current or not?
yeah.
Okay, so what he is doing is he made the coil, right, and trying to move the magnet within that. Nothing has happened.
Yeah.
He spent days and days and days, and one day when he's frustrated, he just throw the magnet on that coil.
Yeah.
Okay, and because the speed is too much on the coil of the magnetic bar, the flux generated.
Oh,
This galvanometer fluctuated a bit.
yeah.
And then he again repeat this experiment by moving the flux, or sorry, by moving the rod, either making close to it or taking far away. In both the directions, the electric current produced or induced.
Okay.
Okay, so this is what they are trying to say when we are talking about magnetic flux as such. Okay, this is the calculation of the flux. B into A is the, so again, when we are seeing cos theta or BA as such, or anything which is related to an angle, because it's not just we can move within that particular, it can be anywhere,
Yeah.
right? Within that particular field, it can be anywhere. So that's the angle that we are talking about, or that the component that we are talking about.
Right. Okay.
Okay. So, so it is also understand that it depend upon the magnetic field variation. So if we have a strong magnetic field, it will, and the movement of that bar is constant, but the magnetic field is constantly changed, then also the flux will generate.
Okay.
Okay, so two things is happening here. One is we can induce the current while moving the coil itself
Hmm.
within the speed, or we can change the magnetic field. So if there is more, less. So
Hmm.
this is what this yellow thing is explaining, that same thing. Varying magnetic. Each point on a surface is associated with a direction called the surface normal. The magnetic flux through a point is then the component of the magnetic field along the normal direction. So here the magnetic field direction is changing. So now the key point is when we are dealing with some vector units, right? Vector units are units which not only have the magnitude but also the direction,
Okay.
right? So for example, speed is a scalar quantity, but velocity is a vector quantity.
Okay.
All right.
Yeah.
So that means when I'm talking about speed, what's the speed of the car? It is 60 kilometer per hour.
Yeah.
Okay. But when I say which way, right?
Mm.
So it's become automatically become vector.
Ve-
It all become velocity. So
Right.
that's the way that we have, because we haven't talked about that particular thing, the vector and the scalar quantities. So it may be pretty a little bit hard to understand that why the directions got changed and the value of that particular component is also changing, right? We will see in couple of other chapters or next chapters that why it is. But for now onwards, it just you just need to remember that vector quantities has directions as well. So even if the magnitude is same,
Yeah.
but the direction is changing, that means the quantity is changing as such.
Okay.
Okay. So Faraday's law of induction and Lenz's law. Again, now I want to see the calculation that I'm pretty much interested in, that where we got that bit complex theory, but at least we can come up with that one. Here it is. I will draw something tomorrow with some more detailed explanation of this thing,
Okay.
right? So that it makes some sense to you, because otherwise going through from page to page, it will be not much helpful to understand that why we have EMF is equal to PVL or V is equal to VIL. Okay,
Yeah.
so that's the main point that we have to cover up tomorrow. Other than that, I believe that we have covered all the topics, touch-ups regarding to the level 2 physics,
Yeah.
right, which is being coming up in our next chapters. And also tomorrow, once I explain these two topics collectively, and we will spend like 10-15 minutes going through with this,
Yeah.
right? Because this is also, they are saying that this is the touch up, but I think it is the summary of level 3, uh, what we know as such. Okay.
Okay.
So we cover the capacitors. Okay. Stuff you should know from level 2. So this is basic electricity, means that we have to know something from level 2. From there, from here, we will going to start the insulators and conductors.
Okay.
Okay, in detail, this is the cover up of all those things that we already, we haven't done much about that. All right, and
Yeah.
then we will come up maybe on Thursday and Friday, we will do some numericals.
Okay.
All right, so that will be complete set of electricity that we can come up with that.
Yeah.
So it will took around, so as per our speed, I think that if we try to cover up with 3 classes or 3-hour classes for theory and 2 hours for numericals, that will be enough for our chapters.
Yeah. I think that sounds
Okay.
good.
So and it's also like, because it's new to me as well, so I need to put more time to configure and formulate some interesting interesting way to make you understand,
Okay.
right?
Yeah.
I'm trying my part, and I will I will expect same from your side. So
Yeah.
try to do the assignments
I'll
so
do.
that I can understand that you are making some progress in that particular way.
Yeah.
For today, I will like you to do some questions related to resistance. Mm, I will send you an email with couple of questions,
Okay.
right? To not complex, but at least simple calculation of charges and times, that what we have learned so far.
Yeah.
Okay.
Okay.
By the end of the day, you definitely have those things.
Okay.
Cool.
Yeah. Sounds
All
good.
right, buddy. Thanks for your time again. And sorry, I took some more, pretty much more time to explain certain finds and facts. I haven't prepared much for this. I thought that it will be easy for you to understand, but it's my mistake that I have to make more clarified explanation
Yeah.
to you for those particular terms. Okay, I will take care of that in
Yeah. That's okay. Thank you, Mandeep.
Thanks, Jiran, and please be vigilant with those 6 assignments that I have given to you.
Yeah.
Okay.
Okay.
See you then. See
See
you
you tomorrow.
tomorrow.
Yeah.
Cheers.
Bye.
Bye.